Hi everyone, I'm Katya. I record this video for Big Ideas in Dynamics. In this video, we're going to talk about one section from this book, Dynamics Beyond Uniform Hyperbolicity. So this is section 7.3, subsection 7.3.1, Pathological Central Foliations. Today, I'm going to prove a lemma, which is important for the proof of the following theorem by Shub and Wilkinson, which tells you that there exists open subset of C1 volume-preserving partially hyperbolic diffeos of 3 torus, such that they admit unique central foliation, which is not absolutely continuous. So first part of this video is recorded by Marisa Cantarina, where she discusses this theorem, how to prove it, and also she gives lots of definitions for partially hyperbolic systems, for foliations, for central foliations, what it means to be absolutely continuous, and so on and so forth. So please check her video. I will share the link down below. This theorem relies on a lemma, and I'm going to prove this technical lemma here. Okay, so let's actually define what we study. Okay, so let me consider first H is automorphism of 2 torus, which is a linear Anosov diffeo. Anosov area preserving diffeo. Now I'm going to define F as H times identity. So it's just a definition. So this is a map on the 3 torus now. So identity is a map on the 3rd coordinate. So F of x, y, z is H of x, y, z. So 3rd coordinate stays the same. This map is will also be linear, volume preserving diffeo, right? Okay. So this map F, so if we take df, right, it's going to be, so it's a linear map, so it's going to be just a constant matrix. So df has 3 directions, which is stable, unstable, and neutral. So stable and unstable directions, we just have them from the fact that H is Anosov, right? So df acting on ES, so let me fix notation, it's lambda ES, okay, lambda is eigenvalue of matrix H or matrix F as well. Okay, so lambda is bigger than 0, smaller than 1, smaller, and 1 is smaller than lambda inverse, right? So lambda and lambda inverse are 2 eigenvalues. So matrix H is matrix with determinant 1, so it's area preserving. So then df acting on unstable is going to be lambda inverse. Unstable, okay, stable direction, unstable, and then df acting on the central is going to be just central, okay, central or neutral direction. So this is our original map F. So now we're going to construct, so this is original map. So now we're going to construct its perturbation. And now perturbation. Okay, so let me define it as phi. That's my perturbation acting on the 3 torus again. So once again, I want it to be volume preserving diffeo. Okay, I define phi in the basis of E stable plus alpha central, unstable for some alpha bigger than 0. So be careful, in the book, it's defined a little bit differently and it doesn't work out. So in order to have the correct proof, I believe we have to define it this way in the basis. Okay, so phi of x, y, z in this new basis looks like x plus psi of y, and z. So really what it means is just x, y, z, as you can see, plus psi, that depends on y only, times this vector, es plus alpha ec. Okay, so what is psi? Psi is just a function from 1 torus to another such that it's C1 close to 0. So it's really just small perturbation, C1 small perturbation, right? But then it's a perturbation along this direction, stable plus alpha central. Okay, so in order for phi to be automorphism of 3 torus, then we need to ask that psi actually, so psi will preserve the lattice. Then it's a good map on the 3 torus. Okay, so let's assume that is done as well. Okay, now define G. So this is my original map, right? So this is my F, then this is my perturbation phi, and then this is my map. The map of study is G, which is F of phi. Okay, and the lemma we're going to prove is this one. If psi is not a constant, identically constant, then the integrated central Lyapunov exponent, let me call it lambda c of G, which is just defined by central log G on the central of G, d mu. Mu is the bag measure, so mu is negative. So this is the part that we're going to prove, that this Lyapunov, the central Lyapunov exponent is now negative. Well, so how do we get it? You can see actually that, like, the idea is that what we do using this map phi is that we somehow, like, we don't touch really the unstable direction at all. So really the central stable direction will be invariant, right? So it's still, so my perturbation really preserves the central stable direction. And we somehow mix in central direction and stable direction. And from the stable, because lambda is smaller than 1, the stable Lyapunov exponent really, it is negative. So the central is 0 originally for original F. But now we're mixing somehow central and stable directions. So we're getting this negative central Lyapunov exponent as well. So that's the main idea. So we're going to prove this lemma. Okay, so let's start the proof. So dg is going to be df times dv. So this is the chain rule. F is linear. Okay, so df. So let's compute df first. So for df, we know that in the basis of, so in basis of stable, central, and unstable, it simply looks like lambda 1 and lambda inverse. All the rest are zeros, right? That's in the basis of stable. This is exactly my eigenvalue corresponding to the stable, and lambda inverse corresponding to unstable. Okay, now I'm going to compute it. So we need to compute it all in the basis of ES plus alpha EC, EC, EU. Okay, so df in this basis, well, so how df is acting on ES plus alpha EC? Well, this is df on ES plus df. Well, alpha is just a number acting on EC, which is, well, we know how it acts, is really lambda ES plus alpha EC. I'm going to write it down in terms of in the new basis. So what I get is lambda times ES plus alpha EC. Then, well, so I added alpha EC times lambda. So I have to subtract it, minus lambda alpha EC plus alpha EC. So what I get is lambda ES plus alpha EC minus, plus alpha times 1 minus lambda EC, right? And then this is the same plus 0 times EU, right? Well, let me continue. So df acting on basis vector is EC is the same as just EC, like 0 times ES plus alpha EC plus 1 times EC plus 0 times EU, and then df acting on unstable. 0 times plus 0 times CC plus lambda inverse EU. Okay, so these are my coordinates, right? 0, 1, 0, 0, 0, lambda inverse. Okay, so df looks like in this new basis, like lambda. Then this is my second coordinate, alpha times 1 minus lambda, 0. Then this is 0, 1, 0. And now 0, 0, lambda inverse. In the basis, ES plus alpha EC, EC, EU. Okay, so this is how my DF looks like in this basis. I want to introduce notation, which is A. It's alpha times 1 minus lambda. So it's clearly bigger than 0. Alpha is bigger than 0. Lambda is smaller than 1. So P is given by x plus psi of y, y, z. Okay? In this basis. EC, EU, d phi in this basis. So this is my phi1. This is my phi2, phi3. So my d phi is going to be d phi1 over dx, dy, dz, and so on and so forth. This is 1, then psi prime, then 0, then 0, 1, 0, 0, 0, and 1. This is in the basis of ES plus alpha EC, EC, EU. Okay, so now if we take df, so we just multiply dg, df. So we're going to multiply df matrix A1, 0, 0, 0, lambda inverse by this one. Psi prime 0, 0, 1, 0, 0, 0, 1. Okay, so what we're going to get, so it's just lambda, then it's lambda psi prime, 0, a psi prime plus 1, 0, and 0, 0, lambda inverse. Okay, so this is the matrix we get. This is our DG matrix. So what we're going to do is the following. So we know that phi is actually the small perturbation. So let's look here. So phi is actually the small perturbation of original map F. And this stable central foliation is preserved. So that means that if we look at the central direction for F, then, okay, so the vectors in the central direction of F looks like 0, 1, 0, right? This is exactly the central direction. But that means that the vectors in the central direction for G will really look like, well, we do not touch unstable at all. So this is going to be 0 as well. And then we can make it in a way that it's 1 and omega. Omega is a function. It's a function on a 3 torus to R. And this is C0 close to 0. Well, why? Because this direction will depend continuously on perturbation. And so our perturbation was small. So that's why this function that is presenting the central direction for our new will be C1, C0 close to 0 as well. So let's apply dg to this vector, omega 1, 0. So what do we get is the following. Okay, so let me compute it. 0, 0, lambda inverse. Okay, omega 1, 0, lambda omega plus lambda psi prime. Then the second line is a omega plus a psi prime plus 1. And the last line is 0. Okay. So By invariance, dg, really acting on omega 1, 0, can be written as this jc times omega of g 1, 0. Okay? So by the invariance of central foliation, jc of g. So omega of g, looking at this expression and this one, just comparing it, we see that jc is really a times omega plus psi prime plus 1. Okay, so let me tell you that I'm looking at omega as a function on 3 torus. So we considered psi, which is here, as a function on 1 torus, but you can lift it. So lift psi. I will denote it by the same letter to the 3 torus, such that it's exactly psi on the 1 torus depending on the coordinate y, but then it's just a constant along the other. And now looking at omega of g is going to be lambda times omega plus psi prime over my Jacobian a times omega plus psi prime plus 1. I'm going to just introduce this notation. Omega plus psi prime is t. And now note that lambda t over at plus 1 is actually smaller or equal than lambda t for t bigger than -1 over a. Okay, so what is true? So lambda is just a number that is positive. It's bigger than 0, smaller than 1. That was the fixed number, right? So it's positive. So we can ignore it. And now if you look at the so if you look at the graph of the function t over at plus 1, so this is really just a hyperbola, and it goes through the point. So when t is 0, then this is 0 as well. Horizontal and vertical asymptotes at okay, t equals negative 1 over a. This is the vertical one, right? And then t equals 1 over a. This is the horizontal one. This is my hyperbola for this function. And then t is simply this. So my hyperbola is really under this graph of t. So that's the that's how you can see this inequality. And really we have this equal to each other. So lambda t, so with equality, so we have equality if t is 0, right? So this is the only point where we have this equality. Okay, so what it means? It means really that my omega of g is, which is, okay, so let me rewrite it, over a omega plus psi prime plus 1 is smaller or equal than lambda times omega plus psi prime, with equality only if omega plus psi prime is 0. Okay? So now I'm going to integrate this inequality. Integral of omega of g with respect to my Lebesgue measure on the 3 torus. This is smaller or equal than integral of lambda omega plus psi prime d mu. Mu is the Lebesgue measure on the 3 torus. Okay. I know about this integral that I can actually do a change of variables. So it's going to be d mu of g inverse. But then because g is measure preserving, g is volume preserving. Okay, so now, so here I just change variable, but then g is volume preserving. That's why it's equal to the integral of omega d mu. Okay, that's it. So now I'm going to use the fact that if I integrate my psi prime over 3 torus, I'm talking about lift, but this is really the same as the integral of psi prime, where psi prime is now a function of one variable only, over d mu on the 1 torus, right? But this is really what? Well, so this d mu is really just a d. So this depends on y, this is dy in the 1 torus. So it's really the integral of d psi. So psi is, by definition, psi was a C1 close to 0. So we can actually, so it gives you the form on a 1 torus, right? So now I can use the Stokes theorem to say that it's an integral over this of psi, right? And then, well, this is just an empty set, so it's going to give me 0. So the integral of my psi prime over 3 torus will give me 0. So let me just move this part a little bit. So I can actually say, using this equality, that this integral is equal to 0. It's integral of omega plus psi prime over d mu. Okay, over 3 torus. Okay, so we got it. So now let me take this part and this last part. This integral d mu smaller equal than this one, lambda times omega plus psi prime d mu. And we have equality here only if omega plus psi prime was just 0 everywhere. Well, that's because we have this here, we have this equality only if this is 0. What is omega plus psi prime? Let's get back to here. So omega of g, it means that omega of g is actually 0. Everywhere, right? But then from here, it means that omega is really 0, right? But then it really means that if omega is 0, then psi prime is 0. So, but then it means that psi is just a constant. And that's a contradiction because we assume that psi is not, let me look at this lemma. Yes. So we assume that psi is not a constant. So this is a contradiction to hypothesis of our lemma. So we don't have this situation of equality really. So we have, so from here, okay, so we get that integral d mu is strictly smaller than the integral. Okay, so let me put lambda outside. Omega plus psi prime d mu, 1 minus lambda integral of omega plus psi prime d mu is smaller than 0, but 1 minus lambda is actually positive because lambda is smaller than 1. Okay, so we got this integral being negative. So now let's get back to computing central Lyapunov exponent of g. So that's our formula. So we take natural log dg on the central d mu is really equal to the function g, our Jacobian of g. So by choice of Riemannian metric. And Lyapunov exponent doesn't depend on this choice, so it's okay to choose whatever we like. Okay, so this is integral of natural log of our gc of g d mu. And let's get back what it is. Right here. So it's a times omega plus psi prime plus 1. A integral a times omega plus psi prime plus 1 d mu. Okay. So now I'm going to use this inequality ln omega 1 plus x smaller or equal than x. Well, that's really true for x bigger than -1, right? So this is my x. So really when x is 0, then it's 0. So this is the, oops. So when x is -1, that's my asymptote. Okay, so this is the graph of ln 1 plus x. This is, again, my x, y equals x graph. So this ln 1 plus x is going to be right below x, y equals x. Okay, so this is true. And in our case, we have this omega plus psi prime bigger than 1 over -a. So this is bigger than -1. So it makes sense. Okay, so here we have it smaller or equal, this integral smaller or equal than the integral of a omega plus psi prime d mu, which is a times, well, a is the number that is bigger than 0. We discussed that. D mu. And this is smaller than 0, it's negative. So that's the end of the proof. Central Lyapunov exponent is negative. Okay, so really what we've done is the following, that we somehow mix the stable and central directions, leaving the unstable just the way it is. This small perturbation really gave us this shift of the central Lyapunov exponent into negative. Let me know if you have any questions, remarks, or comments.